Hello, and welcome to Observing Chaos, how distributed tracing brings observability to a service mess. My name is Juraci Paixa. I'm a software engineer at Red Hat, and I work on the Chiali project. Chiali is a service mesh observability tool, and among other things, it features integration with a distributed tracing tool called Jaeger. I'm also a maintainer on the Jaeger project. For the session here today, we're talking about three concepts that might be new to some of you. So the first one is Servicemashes, and then observability, and distributed tracing. So we're spending the first part of this session talking about this, the concepts and the theory behind that. And then we have a very short introduction to the tools, Istio and Jaeger, and we are using those tools on the demo at the end of the session. And we should have enough time for a Q&A, but if we don't have that much time, then feel free to come to the Red Hat booth afterwards. I'll be there, and I'm more than glad to discuss that with you. All right, so let's get started. And let's start with then Servicemashes. So to understand why we need Servicemashes and why they're good for, we have to keep in mind that our main context here are in our microservices, right? So, but don't worry, I'm not going to explain to you what microservices are. I know that you had quite some of those introductions over the past years, so I'm not going to explain to you what they are. What I would like you to keep in mind, though, what I'd like you to focus on is that they are just distributed systems. And as such, they fall for the 8 fallacies of distributed systems. Now, if you've been doing microservices for more than a couple of months, then you know all those 8 fallacies already by heart, right? In fact, they're really not new. They're decades old. And if we take one application or applications that we've built 4 or 5 years ago, and we crack that jar open, so what do we see there? We see a Java Spring Boot application that embeds some libraries, right? So we see Eureka there for service discovery. We see Hystrix for resiliency. We see Ribbon for load balancing, and perhaps even some Zool for service gateway. Now, that works quite well. But at least to me, one of the main advantages of microservices is that we have the freedom to use the right tools for different jobs, right? So perhaps we have one workload that is really the best use case for using Go. How do we make sure that the libraries that we use in Java are compatible, or at least in the same level, or consumes the same kind of metadata that our Java libraries are using, right? So we have to hunt for libraries that are compatible between codes, right? And that's especially true for service discovery. So we don't want our service discovery metadata to reside in 2 different systems. We want only one of them, because otherwise they would just get out of sync. Now, once we find that specific set of libraries that work both for Go and for Java, and that we can reuse this data, then we start thinking about Ruby or Python or Node.js, right? So we have the same question over and over for every language we have. Then we might change our question. So perhaps our question now is, what if we could delegate some of those tasks to our middleware instead? Now, middleware here is between codes, because we would probably use the word platform nowadays, right? We typically don't deploy things on middleware anymore. We deploy our applications as a runnable or executable unit directly into our platform, like Kubernetes, for instance. Right? So, and the answer to that question is exactly the context for Servicemashes. If we look it up on Wikipedia, it says that a service mesh is a dedicated infrastructure layer for facilitating service-to-service communications between microservices, often using a sidecar proxy. Now, this is quite easy to digest, I guess, right? Except perhaps for the last line here. So sidecar proxies. So for those of you who are not that familiar with Kubernetes, a sidecar proxy is the second container that we have inside our pod. So you see, when we deploy things on Kubernetes, we have our microservice image, so we have our container image, and we specify in a YAML file that we want to deploy that container image, and we specify some configuration for that, like how many replicas do I have for this deployment. Kubernetes then converts that desired state with the actual state. And it does that by executing the same pod, or it creates a number of pods, and within the pod we have a container. And typically we have one pod per container. Now a sidecar is the second or an extra container within that pod. So it's not part of our business. It's not, the core of the business for that pod. And it's typically something that would benefit from being very close to the application. And that's the case for a proxy. So the sidecar proxy is then a container that intercepts all the communication going in and out of the pod. And those sidecar proxies, now we have sidecar proxies then for all the pods here. And all those sidecar proxies are then connected to a mesh controller, a head. So whenever there is a change in the topology, the mesh controller gets notified or recognizes this change. And it might send an update event to all the proxies. So all the proxies know about the topology at that specific point in time. Now, once we have this kind of architecture in place, it's kind of easy to imagine that we can program our mesh controller, right? We can change the configuration for our mesh controller to program our network. One example would be to do A/B tests, right? So now that we offloaded all the networking decisions from our application and that it's all now part of a mesh configuration, we can configure our mesh to send 50% of the traffic to a hypothesis 1 of a new version of the service bar, and the other 50% to the hypothesis 2. And then we can collect metrics from those pods and see which version wins in production, right? And once we have that answer, then we can change the mesh configuration again, setting that we want then the winner, like hypothesis 2, to receive 100% of the requests. So that's the classic use case for service meshes, right? So that's why that's how we use service meshes out there. Now, some of you might be wondering, is it worth it? I can see so many downsides, right? I can see some downsides as well. So the first one is quite obvious, and I can't even believe that I left the point there on the slides. And it is that the more software we have, the more bugs we have, right? It's that simple. So whenever we apply something new, we have to deal with the bugs that that piece of software introduces. Now, the second point is also kind of obvious, and that nothing really comes for free. And we have two ways of seeing that. The first way is that the classic one, like we have a new software, so we have the need for someone to run this software, to install it, to maintain, to patch it, to wake up at 2 a.m. to fix problems. Now, the other part of this point here is more specific to Servicemashes, and that is, imagine we have now two microservices that previously were talking to each other directly. Now they're talking through proxies. Even if those proxies are not doing much, they're still doing something, and something costs, right? So you are paying the price for that. And if you have a very time-sensitive, performance-sensitive application, then you might think twice before using service meshes. Now, if your service bar takes, I don't know, 1 second to return, then 10 milliseconds is not that big of a problem. Then, to me as a developer, the third biggest downside is that I have now a higher intrinsic cognitive load. And that means that whenever I think about my application, I don't think only about my application anymore. I think about my application in the context of service meshes as well. So when I have a new problem or when I have a new feature, I have to consider service meshes in the architecture of this new feature. I have to consider that there might something might happen that is relevant for service meshes, or I might want to design things in a different way because of that. And then the final point is that debugging is harder. Now, debugging is harder because, the developer setup is different than the production setup. Now, if we go back like 5 years ago, we would hear people saying, well, containers are there so that we can build things exactly the way that we run it in production. Right? So that was the basic premise of containers. But now we are at the point again that our development setup is quite different than our production setup. And it makes debugging harder. Now, the second point of why debugging is harder is that we don't know exactly why things are failing, or at least we don't know at first sight. So if a request fails, it's harder to answer why did this specific request fail. Is it because service foo is now talking to an incompatible version of service bar? Or is it a network failure at the proxy level? So where is this failure? Why is it broken? Now, we are coming back to this point later, and I'd just like to leave a hint here, and with the word observability. So keep that in mind. And the final point on why debugging is harder is in previous generation microservices, we would probably just increase the logging level. And if we were smart when we were coding our application in the first place, we would add a debug statement to our code whenever we make a downstream call. Right? So whenever we call some downstream microservice, so that we know what is the IP address that we are trying to talk to. So what is this other service? Now, it doesn't matter how many, it doesn't matter what is our logging level now. This decision is not made by our application. This decision is now made by the proxy, and we have no access, to the proxy from our application. So there's no way for our application to know what is the actual host that it's talking to. And that makes debugging harder. Now, those last two slides might scare you off of service meshes, and that's not my intention. I think that we have to understand why we are doing things and what is the price of doing things. And to me, as a developer, those are the prices, right? And that's what we are giving up on. But we are doing that to gain access to some features. And service meshes, I would say that we divide in 3 categories, the features for service meshes. One of them we saw are A/B tests, and that is in the category of smart routing. Now, applying the same techniques, we can do some canary releases or blue-green deployments, and we might even do some traffic mirroring. For instance, we have a new version of our service, and we want to see if it can scale the same way as the previous version. So we direct the traffic to both services at the same time. One is hidden and one is live. The second category is resiliency. So before we had circuit breakers at instance levels. So if we have 10 instances of our application, then we have 10 circuit breakers. Or, depending on the tools that we're using, we have one circuit breaker for that application and shared across all the 10 instances. But it's hard to find a tool that can make a circuit breaker cluster-wide, right? And that's relatively easy to do with Servicemashes. You can do circuit breakers on a cluster-wide basis. And on the resiliency category, we can do retries, timeouts. We can apply some chaos engineering with fault injection. But to me, the real killer feature is in the realm of security. So because all the networking decisions are now in the proxy, we can use the same set of certificates for all the proxies, and then we have TLS enabled across our cluster. Right, so before we had to deal with certificates and keys and CAs and provisioning of all of that and rotation and reloading. Now that it's down to the proxy, we don't need to care about that anymore in our applications. And yet, we can benefit from traffic encryption, or even mutual TLS, where not only the server is authenticating with the client, but the client is also sending a certificate to the server. We can also apply some traffic policies, like service foo can only talk to service bar, 1,000 requests per second. So that's the theory behind Servicemashes. That was a crash course on Servicemashes, or at least the theory. But I'd like to go back to one of the points that we talked before. So answering the question why certain requests are failing. And we can apply the concepts of observability to understand why things are failing. Now, before I move on, we should probably define what observability is. If you go back to Wikipedia once more, we see that they define, or it is defined there, that in control theory, observability is a measure of how well internal states of a system can be inferred from knowledge of its external outputs. How about we translate that to microservices? So when we talk about microservices, we could probably translate that as we can infer the state of our architecture, of our application, based on the outputs that we see from our microservices. Is it better? So perhaps we can, so what are those outputs? So some of those outputs might be metrics. So whenever we receive a request, we hit a counter, right? So that's one output from our application. Or the logs, we can analyze the logs. Or we can analyze the traces, we can collect tracing information. Now, one key thing here is that we talk about observability in the context of distributed systems. We typically apply observability when we have dozens of services, and each one of those services are potentially at different versions, and we might have a couple of replicas for each of those services. Now, when we do the math, we come up with the result that what we have is chaos, right? I mean, we have dozens of services at different versions and different replicas, so we don't know who is talking to whom and at which version. So that's why observability is so important in a distributed systems context, or more specifically for microservices, because it is exacerbated by microservices. Now, I believe that all of you know what metrics are, and you use it on a day-to-day basis. I know you know about logs as well, of course. But what about tracing? So who here is using tracing on their production applications? Okay, that's more than I expected. That's good. So what is tracing? So tracing is the technique that we use to tell the story of a request across services. So imagine the example that we saw on the workflow on the very first slides, that we have foo and we have bar. Right? Now imagine that we are zoomed in, and then now we zoom out. And we see that bar is also making a call to a third service. And based on its outputs, it makes some database calls. Now, tracing is a tool that we can use to visualize that we have a request going to foo, and then to bar, and then to a third service, and then the database calls. So tracing can show you this whole transaction chain. So basically it answers which services were touched, when, and in which order. Now, the way that tracing works is by measuring units of work. And we typically call those units of work spans, right? So that's a tracing a specific term. And a span is nothing more than a data structure where we store what is the name of this unit of work, when did it start, how long it took, and perhaps some metadata about the unit of work. If you're talking about a HTTP request, for instance, then we might want to store what is the URL for that unit of work, for that HTTP call. Or what was the status code that we returned to the caller. If you're talking about a database call, then we might want to store what was the actual query that we executed, right? Spans may contain references to other spans. And once we have that, we can imply causality. So back to the example, foo calling bar, calling a third service. If it were not for foo, if we did not receive a call on foo, then there would be no database calls at all. Right? And we can imply this causality by the references between spans. So we can see why certain things were executed by looking at the chain of events. And it works by building on top of context propagation. So context propagation, our context here is basically a set of IDs, right? At the base level, it's only a set of IDs, like the trace ID and the span ID. And tracing context propagation might happen either very explicitly, so we pass it, whenever we make a method call, we pass the context along, or if you're using a model that supports it, we can store the context in a thread local storage, for instance, and then we manipulate that thread local storage based on our necessities in terms of spans. And then when we go remote, like from foo to bar, when we make an HTTP call, we serialize the context on our caller side, and we deserialize the context on the server side. Now, in terms of HTTP, it means that before we call the external service or the downstream service, we serialize this context in one HTTP header, and then we send this HTTP header with the payload to the other service. And now on the other side, we look at that HTTP header, we deserialize, and we have a new context there. Whenever we start a new span there, it sees that it belongs to the same trace ID that we had on the first service. When all those spans reach a common system, we can now see then this whole trace on this UI. Now, the final goal with tracing is to come up with a call tree or call graph similar to what we have here on the left-hand side. Now, this is a very typical directed acyclic graph, right? So nothing really new. It's pretty standard. perhaps what is interesting is that we typically plot this data as a Gantt chart. Right? So because the timing information is probably the most important thing in this whole thing, then we plot that as a Gantt chart. So we can see how long an operation took and what are the dependencies. Right? So what are the child processes for that one. Now, there is one missing piece to that, and that is, how do we create those spans? So how are they defined? So who creates them? And typically, the spans are created by the tools that you use, just like logging, right? So logging, you use some framework, and that framework then outputs quite a bunch of stuff to your log files. The same with tracing. You can use some tools that auto-instrument the stack that you are using, and spans, if everything is configured properly, then spans are just being then reported to the external system. When we are using a service mesh, then the service mesh could be generating spans as well, right? So you can have spans at the service mesh level, at the platform level, and then at the framework level. And then, if you find it useful, you can also create spans that are specific to your business. So in the example that we have here, it is a typical JAX-RS endpoint, nothing really special. And we can measure how long that one took by wrapping our code in a try with resources statement. Right? So we get a tracer bin from somewhere, and we build a new span. We give a name to the span, so submit order, and then we call the start method. When we call start, we start measuring we start the clock, right? So we start measuring time. And then when we step out of this try with resources statement, Java calls, or the JVM calls, the close method, and then we stop the clock watch. So we know exactly how long it took for this one here to execute. Now, we can also enhance our span by adding some metadata about our business. So we can add a tag saying that this is a high priority order. All right, so that's it for the theory part. And we have now a very short introduction about the tools. And we then follow with the demo. So for Istio, there is not much left to say. I mean, Istio is pretty much the standard or reference implementation for Servicemashes. I think it's, if not the first, it's one of the first ones. But if you look at other Servicemashes, the architecture follows quite closely. And this graph that we have here matches very closely to what we saw before, right? So 2 services at the top, each one of them with a proxy, and those proxies connected to a in this case here, it's called the mixer, but we don't care about the names here. We just know that it's the service mesh, right? Now, Istio might be useful or used outside of Kubernetes, but I have not seen that yet. And the way that you interact with Istio is the way that you interact with Kubernetes or Kubernetes-based applications, and that is by applying YAML files. So let's see how we can achieve a couple of things with Istio. So this is a fault injection scenario. So what we want to do here is we want to add a fault between a connection of client and server. So we want the server to wait 10 seconds and then fail. Right? So some chaos engineering here. Now again, just to recap, there's no change to the code in our client or in our server. It's only about the mesh configuration, and that is not a development concern. It's not something that we think about when developing. It is a thing that we think about when during runtime, during the operations time, right? So when we are operating our software. And we can do that by applying a YAML file like this one. So if you've done some Kubernetes before, this might look familiar. So we have an API version, we have a kind, we have a name, metadata with a name, and we have a specification. And then within the specification, we say, for all the calls to the server version 1, I want to apply a fixed delay of 10 seconds on 100% of my requests. And that's it. Once I apply this YAML file, once I do kube control, apply -f, and a file with these contents here, I see the requests piling up before my server. The second example that I have for you is my favorite use case. It is, I think, one of the killer features for Servicemashes, and that is mutual TLS authentication. So how many of you have implemented or had to use mutual TLS between microservices before? A few people. And how many of you did that because it was fun, as opposed to you had to do it? Yeah, I thought so. The thing is, it's not fun to deal with TLS certificates, right? So you have to provision them, and you have to provision in a way that it's issued by a trusted certificate authority. And trusted is in itself something vague, right? So what is trusted for your cluster? And then once you get the certificates, once you have the keys, and once you have the CA bundle, you have to think about how to store that securely. And now, once you have that set up, it's not the end. You have to deal with revocations. You have to deal with rotation of the keys. You have to deal with reloading this new configuration while in production. Right? So it's really not fun to do it. But you can do that with Servicemashes or with Istio in particular. You can do that by applying two YAML files. So the first one is saying that my mesh policy is strict mutual TLS, meaning if I'm not doing mutual TLS, if mutual TLS is not possible for this connection, then don't make the connection. And the second one is a destination rule saying whenever I want to reach another service within my cluster, I want to start the connection making the assumption that I'm making a mutual TLS connection. And that's it. Once you do that, once you apply those two YAML files, and you're using a tool like Kiali, then you can see some small padlocks on the connections, right? So Kiali will show you green lines when the connection is healthy between services. And once you have mutual TLS between that, you see small padlocks indicating that that connection is secure. Now, that is just a small capture of the Kiali's service mesh for one specific namespace. But if you open the dashboard, the Kiali's dashboard, then you see also small padlocks close to the namespaces, so that you know that that namespace has mutual TLS configured. Right? So everything happening within that namespace is secure by default. And then the final tool that I wanted to introduce you is Jaeger. So Jaeger is a distributed tracing solution, meaning that it provides you with the client libraries, with the backend components that receive the span information from your applications or from your infra, and a user interface for you to visualize and analyze this data. Now, client libraries, we have three main client libraries nowadays. One is Jaeger proper, and then we have OpenCensus and now OpenTelemetry. Right, so it doesn't matter which one you use. Those are the things that knows how to build a new span and report this span somewhere. Now, this is a logical flow or logical architecture of Jaeger, and it shows how things flow, right? So everything starts with your application. So you use a tracer to create the span, and that tracer sends data typically to a local process that is called the Jaeger agent. Now in Kubernetes, it might be a sidecar, but if you're deploying on bare metal, then it might be a daemon running on the same machine. The agent then sends data to a remote collector that then stores this information in a database. And that database is then consulted when you open the UI. So you open the Jaeger UI, it goes to the Jaeger query component that reads data from the storage. And that's all I had for Jaeger on slides. I would like you now to show you Jaeger in practice. All right, so before starting the presentation, I prepared 3 microservices. So I have, let me show you the code for that actually. So I have here 3 microservices. They are called service mesh order, inventory, and account. Those are Quarkus applications, and Quarkus, if you don't know about Quarkus, then stop by the Red Hat booth and we can tell you what Quarkus is. But if you know MicroProfile or if you know JAX-RS, then this code here is not foreign to you, right? So you should recognize that. It's a JAX-RS endpoint, see the /path here, with injecting some REST client, and the REST client comes from MicroProfile. We inject a second REST client for our second service, so to call the inventory service, and we inject a tracer. Now you might be thinking, where is this coming from? Where is this tracer being defined? It is actually auto-configured for you by Quarkus. So if you add a dependency called Quarkus ~i open tracing to your Quarkus application, then Quarkus brings both the instrumentation libraries, like open tracing, and it brings as well a concrete implementation for you to use, Jaeger in this case. And everything is then configured automatically to you, and the default configuration for the Jaeger client is to send data to localhost on a specific port via UDP, right? And given that you have all of that configured, then things, spans would just then be available on the Jaeger UI. And then we have here the actual endpoint. This is exactly the same code as the slide that we had before. So the try with resource statement with the submit order, our tag with the priority high, and so on and so forth. Right? So no magic here, pretty simple, standard, and everything that I have here is only either POJOs or interfaces, right? So there is no magic anywhere here. Now, once we package and once we deploy that application on Kubernetes, we see that we have, let me run again, yeah. So I have the 3 deployments here, each one with 1 pod, with 1 replica. So I should have 3 pods here, 1 for each service, right? And I have them here. And I see that they have 3 containers each. So one is the application container. In this case, it is the account application. The second container is Istio's proxy, the sidecar proxy. And the third container is the Jaeger agent. Right? So we have 3 processes per pod, or 3 containers per pod. And that's it. So it's deployed on my Kubernetes environment, and I just then going to call my service there. So we have the order submitted and some random IDs. And on this third terminal window, I open a kubectl port forward, meaning that that specific port from that specific service is now available on my local host. right? So as if it's a local port. And that's the one here, so localhost, and we see the services here. So when I hit find traces, we see one trace from a few seconds ago. I think it's too small to read. But if I open it, I see that there were 27 units of work as part of that specific HTTP request, as part of one of those curl calls. Right? And I can inspect and see what exactly happened there. So each color here indicates one service. The very first one is Istio Ingress Gateway. So it is not something from our application, it is something from the service mesh. Our application actually starts only here. Only 14 milliseconds after the service mesh received the request, right? So the service, the curl call hits the ingress gateway from Istio, and from the ingress gateway, it does some mixer checks. So it's probably checking the mesh configuration, and then we get our incoming proxy generating a span saying I see a request, and this request is coming to the node ID. This is the HTTP URL that it's calling. And if you go down here, we see that this is the first point of contact with our application. So this is a span that is recorded by the JAX-RS level or layer, the JAX-RS server in this case. And then the next span that we see is the one that we created manually, the submit order span, right? With the priority high and so on and so forth. And we can see which version of that is being used because we added a tag, a process tag, saying that this is the version 2019 11.6, so it's the date, and this is the build time, right? So this is a UTC time, so this application was built at 2:46 p.m. our time, so 1:46 p.m. UTC. Yeah, I mean, you can see some exclamation marks whenever there is something failing. I'm leaving you curious about that, to encourage you to check the source code and see why things are failing. But yeah, another way of seeing that is as a graph, a call graph. So you can compare traces by seeing this specific HTTP request triggered or generated those spans, but not that HTTP request. So why is it different? Then you can compare the traces easily using the trace graph, right? So we can compare some trace. We can select one, and then, I don't know, one like this, and we can compare traces. But we can dig into this to see why which spans are different and why they're different. But yeah, that's a different way of seeing the same kind of information. All right, so that's what I had for the demo. And before we go for a questions and answers, I'd just like to do a small recap, right? So we use Servicemashes mostly to offload the networking decisions or the network complexity from our applications, right? So doing, for instance, mutual TLS is something very complex to do in our code and also kind of risky. And we offload that then to our proxies. But by doing that, we kind of give up on some visibility into what's going on. And we can apply some observability techniques like tracing, logs, and metrics to regain some of that visibility. Right? I would even argue that once you apply tracing, you have even better information than what you had before. And with that, I'm now open for your questions. No questions? The question is whether this kind of model supports cyclical references. Is that right? The model itself supports. It's only a matter of how you visualize that. Right. So the way that the graph is built, you may contain references to multiple parents, or you can contain cyclical references. But it is not. It is a problem that we have not solved for the UI yet. If you imagine the Kafka scenario, that would be one of multiple parents scenario, but it's very hard to visualize that or to identify what is the proper way of doing that in a generic way. Right? And I think the same applies to cyclical references as well. All right, so if there are no more questions, I'm really happy to keep talking about tracing and observability in general with you at the Red Hat booth. So I should be there this whole afternoon and tomorrow most of the day as well. Thank you.